By 2030, the world could consume as many as 630 billion aluminum cans every year. But even more remarkable is that the metal inside each can be reborn dozens of times over the course of centuries, thanks to an astonishingly enduring cycle: aluminum recycling. For a crushed can to be transformed into brand new metal, it must pass through an extremely harsh industrial journey. Millions of cans are compacted, shredded, stripped of paint and contaminants, and then melted into streams of glowing aluminum. The metal is refined, cast into massive slabs, and rolled into bright aluminum sheets, ready to return as a new generation of cans. Join Factron Process inside a massive recycling plant to witness how technology transforms waste back into an endlessly reusable resource. It is aluminum's ability to be reborn almost indefinitely that has made it one of the world's most valuable materials. Today, aluminum recycling is no longer simply a form of waste treatment. It has grown into a global industry worth nearly $96 billion. Remarkably, around 75% of all the aluminum ever produced in history is still in use in one form or another. In the United States, recycled aluminum now accounts for more than 80% of production, showing that scrap metal has become a strategic raw material for economic development. Recycled aluminum is also found in vehicle bodies, window frames, electrical wiring, household appliances, and construction materials. More than 60% of the aluminum currently used in buildings is estimated to come from recycled material. To many people, it is merely a pile of old aluminum cans. But to the recycling industry, it is a resource mine waiting to be awakened. The journey of recycling aluminum cans begins immediately after the final tab is pulled. Empty beer, soft drink, and energy drink cans are placed in recycling bins at homes, restaurants, supermarkets, and stadiums, or taken directly to scrap collection centers. Depending on the region, aluminum cans may be collected separately or mixed with paper, plastic, glass, steel cans, and other recyclable waste. These materials are loaded onto collection trucks and transported to a facility known as a Materials Recovery Facility, or MRF. At the facility entrance, the trucks are weighed to record the amount of material they are carrying. The entire load is then dumped onto the tipping floor, where loaders and grapple buckets continuously feed the waste onto conveyor belts. Before sorting begins, workers quickly remove lithium-ion batteries, pressurized aerosol cans, small gas cylinders, and sealed containers that could cause fires or explosions inside the machinery. Collecting cans may appear to be a simple task, but it ultimately determines how much aluminum can return to the factory. In the United States, aluminum cans were once valued at approximately $1,338 per ton, more than 6 times the value of PET plastic. That value was high enough to fuel a fraud operation worth nearly $10 million between Arizona and California. The perpetrators transported cans from a state without a container refund program into a state that offered refunds, exchanged them for cash, and collected enormous payouts. For this reason, every can recovered through the proper system helps keep aluminum circulating within the production cycle, instead of being buried with ordinary waste. Once delivered to the MRF, the scrap is fed directly into a hydraulic baling chamber, where a heavy steel door seals shut behind it. Massive pistons immediately drive inward from several directions, generating a compressive force of approximately 118 to 237 tons. Under this extreme pressure, thousands of cans collapse at once, their thin metal walls folding and crushing as the trapped air is forced out. A mountain of bulky containers nearly disappears, replaced by a dense, rectangular block of aluminum weighing hundreds of kilograms. Depending on the equipment configuration, each bale can weigh from approximately 450 to more than 1,100 kilograms. A bale weighing nearly 1 ton contains an amount of aluminum equivalent to around 65,000 beverage cans. Tens of thousands of loose cans are locked tightly inside a compact block of scrap, ready to be loaded onto trucks and transported to an aluminum recycling plant. In the raw material preparation area, forklifts place each bale onto the in-feed conveyor. The steel binding wires are cut and collected separately, while the bale breaker uses rotating shafts fitted with large metal teeth to tear apart the tightly compressed mass of cans. The conveyor then feeds all the material into a shredder powered by approximately 340 horsepower. High-speed rotating shafts lined with metal teeth dig deep into the layers of scrap, continuously hooking, tearing, and hurling the cans against the machine walls. The deafening crash of metal echoes throughout the facility, and within seconds, the familiar shape of the beverage cans disappears completely. At the discharge outlet, a screening system acts as a strict filter, allowing only fragments that have reached the required size of 40 to 60 millimeters to pass through. Any pieces that remain too large are retained inside the shredding chamber, where they continue to endure the machine's violent impacts. The shredding process also breaks open cans that have been crushed shut, releasing trapped water, sand, paper, plastic, and other foreign materials from inside. Leaving the shredder, the material stream passes over a vibrating screen that removes dust, sand, glass, and undersized fragments. Magnets pull steel from the conveyor, while the aluminum continues toward an eddy current separator. Inside the machine, a high-speed magnetic rotor generates a constantly changing electromagnetic field. As the aluminum pieces pass through it, the resulting repulsive force instantly propels them forward, while paper, plastic, and other non-conductive materials fall along a different trajectory. The multicolored aluminum fragments are then fed into a rotary decoating kiln. As the drum rotates, the material is continuously tumbled and exposed to a stream of hot gas at approximately 932 degrees Fahrenheit. This temperature is high enough to break down printing inks, paint, varnish, oil, and the internal polymer coating. The gases released from the paint, oil, and polymer layers are not vented directly into the atmosphere. Instead, they are drawn into a secondary combustion chamber, where remaining organic compounds are destroyed, helping reduce smoke, odors, and toxic emissions before the exhaust gases leave the system. The clean, silvery aluminum fragments are gradually discharged by conveyor into a glowing hot melting furnace. The furnace is maintained at approximately 1,346 degrees Fahrenheit, above aluminum's melting point of 1,220 degrees Fahrenheit, causing each piece of metal to soften, collapse, and merge into the molten aluminum bath below. A single industrial furnace can hold up to around 100 tons of metal per batch. The material is charged in stages to prevent the temperature of the molten bath from dropping too suddenly. Agitators and circulating currents draw the scrap beneath the surface, helping it melt faster while limiting its exposure to oxygen. Even so, some of the aluminum still oxidizes and combines with dust and other impurities, forming a layer of dross that floats on the surface. A heat-resistant steel skimming machine slowly removes this layer from the furnace. Because the hot dross still contains a significant amount of trapped aluminum, it is pressed or further processed to recover the remaining metal before it is returned to the melting bath. Within just a few hours, thousands of individual can fragments have disappeared, replaced by a glowing pool of molten metal. But before casting can begin, its composition must first be carefully analyzed. In fact, recycling aluminum requires only about 5% of the energy needed to produce primary aluminum from ore. Even so, the furnace must be tightly controlled, because every kilogram of aluminum burned away into dross represents both lost material and wasted energy already spent melting it. Although the aluminum has already become a glowing pool of molten metal, it is not yet allowed to proceed directly to the casting area. A technician takes a small sample from the furnace, cools it, and analyzes its composition, because can bodies and can ends contain different proportions of alloying elements. Based on the results, pure aluminum and the appropriate amount of manganese or magnesium are added to the molten bath. The stirring system immediately creates circulating currents that blend the added elements evenly throughout tens of tons of liquid metal. Only after the bath reaches the required uniformity and cleanliness is the aluminum transferred to a holding furnace, where it waits to be poured into the casting pit and transformed into slab ingots weighing tens of tons. Once the molten metal meets the required specifications, the holding furnace carrying tens of tons of aluminum slowly begins to tilt. A brilliant white stream of molten metal pours from the furnace, flows through heat-resistant launders, and enters casting molds positioned above a deep pit. At this stage, the metal flow, furnace angle, and temperature must remain extremely stable, because even a small fluctuation can create cracks, distortion, or internal defects. As soon as the aluminum touches the cooled mold walls, its outer surface solidifies, forming a thin shell around the still molten core. The casting table gradually descends into the pit, allowing the slab to grow longer, while powerful jets of cooling water remove heat from its surface. The pouring rate, descent speed, and cooling water flow must be closely synchronized, so the metal solidifies evenly from the outside inward. If cooling becomes uneven, the slab may develop porosity, hot cracks, or internal stresses that could cause problems during rolling. Sensors therefore continuously monitor the metal level, temperature, and casting speed throughout the process. After approximately 2.5 hours, the final portion of molten aluminum has completely solidified. A gigantic slab ingot, nearly 10 meters long and weighing around 27 tons, is lifted from the pit. A single block containing roughly as much aluminum as 1.5 million beverage cans. After casting is complete, the massive aluminum slabs are placed in a homogenizing furnace at approximately 977 degrees Fahrenheit. The heat does not melt the metal. Instead, it makes the thick, rigid slabs more ductile, allowing them to withstand enormous rolling forces without cracking. The furnace doors open, and the heated slab is immediately pulled out and transferred directly to the rolling stand. Two gigantic steel rolls close around the aluminum block and draw it through the narrow gap. The immense pressure flattens the slab while forcing the metal to stretch farther along the roller table. The roller table then reverses direction, sending the aluminum sheet back through the rolling stand. The gap between the rolls is reduced again, and this back and forth compression is repeated several times. The slab becomes thinner and longer until its original shape is almost unrecognizable. By the end of the process, a slab initially measuring tens of inches thick has been transformed into an aluminum strip only about 0.07 to 0.28 inches thick. The hot-rolled aluminum coil is placed on an uncoiler, and the metal strip is pulled taut meter by meter before entering the cold rolling stands. No longer softened at 977 degrees Fahrenheit, the aluminum must now pass between polished steel rolls under immense mechanical pressure. Two rolls rotating in opposite directions continuously draw the strip through an increasingly narrow gap. With each pass, the aluminum becomes thinner, longer, and harder. Friction heats the surface, so rolling oil is sprayed as a fine mist to remove heat, reduce friction, and prevent the steel rolls from scratching the metal. If the strip becomes too hard, the entire coil is placed in an annealing furnace to restore its ductility before rolling continues. From an original slab nearly 33 feet long, the finished aluminum strip can extend for approximately 6.2 miles, while its thickness is reduced to only about 0.010 inch. Sensors continuously scan the full width to measure thickness and flatness, while cameras detect scratches and circular knives trim away the uneven edges. The removed aluminum is collected and returned to the melting furnace. At the end of the line, the continuously moving strip is tightly wound around a steel core, forming a bright aluminum coil weighing tens of thousands of pounds. Each coil is weighed, assigned a traceability code, and secured with steel straps before leaving the plant. From a gleaming aluminum coil, a new generation of cans begins to take shape at an almost unbelievable speed. The metal coil, weighing tens of thousands of pounds, starts to rotate and feeds a bright silver strip straight into the press. Steel dies strike continuously, cutting the strip into circular blanks and then drawing them into small cups. Just seconds earlier, the aluminum was still a flat sheet, stretching for miles. Each cup is forced by a steel punch through narrow die rings. The metal wall is drawn upward and becomes thinner, yet it must not tear, while the bottom remains thick enough to withstand the pressure of carbonated drinks. After just a few violent movements, the familiar shape of a can begins to appear. This transformation happens so quickly that a modern production line can form about 2,200 can bodies per minute, more than 36 every second. The can bodies are then cleaned, printed, and coated with an extremely thin protective layer before being sent to beverage plants. There they are filled and sealed with lids. Less than 60 days earlier, this metal may still have been part of a crushed can lying in a recycling bin. Now, it has returned to the store shelf, not as scrap, but as a brand new can ready to begin the entire journey once again.